Alright, so I got both the screen share and also YouTube live stream up and running at this point. I'm gonna close my YouTube browser right away because I don't need it to chew up extra resources. And I did enable voice chat so you guys can actually use a voice to ask questions. The reason is I found that it doesn't make any difference. The cap or the upper limit of how many people can join the screen share session is still 50, regardless of whether I enable voice chat for you guys or not. So I might as well just re-enable it so that you guys can use your voice to ask questions if you want to do that. All right, so let me get the other parts of the class set up. So the lab is going to be, well, today's lab is not really a lab anymore. It is more like an assignment. Um, I do not doubt that some people would be able to finish it um, within the lab time, but I think most people would need a little bit more time to get it done. So that is going to be, it's going to be an interesting thing because some people may procrastinate a little bit too much until like a few hours before the due date, which is going to be problematic because it's going to be next Tuesday, at 9 a.m. That's next Thursday. I'll make it 1 week as a due date. So people who procrastinate may not find enough time to actually get it done in time. So I'll mention that once the class time starts, but the recording is on already. So all right. So if you guys got any questions to ask, we got about 2 minutes before class actually starts. All right. So if you don't have any questions, I have to tell you yesterday was interesting because in my neighborhood they have one of those utility poles getting replaced, and the job was supposed to end at 6 p.m., but normally they usually end at about 4 p.m. They're pretty efficient. But they encountered a snag in the morning, so they got a late start. So the utility or the power did not come back until like 6, maybe 6:30 or so. And I got a class to teach, a synchronous class just like this one, CISP310 to teach, starting at 4:30. So I was going like, there's no power, there's no wired internet. How am I going to teach this class? So my laptop computer, which is actually what I use, on a daily basis, and this is, I'm using it right now, had a fairly good battery. I mean, once it's charged, it can last actually, like 7-8 hours easily. So there's that, and then I use my cell phone to tether, use USB tethering to go online. And I was actually surprised that the bandwidth of my 4G connection, is actually good enough to do what I usually do, which is including the screen share on Discord and also the live stream to YouTube. So it was actually able to do both without, at least nobody complained about any quality issue. So that was interesting. Terrence has a very good question that most people would ask, and I honestly do not know. I will attempt to get it done in a week, but given that I have an extra class now, and also given that the union responsibility that I have is going to ramp up, I'll talk about that in just a little bit. I'll try to get it done as soon as possible. I revised my system of grading, and hopefully it's going to be a little bit faster these days. But that being said, I can give you the answers. I can give you all the solutions to your specific set of questions fairly quickly. I just have to change my script to generate. It's already generating the solution. I just have to distribute it to you guys along with your own test in read-only mode. So that way you can kind of check your response against the solution. So that hopefully will give you some idea of how you did in the test. Oh, okay. Yeah, absolutely. Your copy of the exam is yours. I mean, I have no there's no point in keeping it, as a secret because I don't really reuse questions. Now, yes, I did reuse questions, okay? Um, okay, somebody's mic is on and there's a little bit of buffering. So anyway, you might have noticed that this test is identical to the practice test. And somebody will say, but my bit patterns are different. Okay, so let me see whose mic is on and alright, so I see a few people have their mics on, but most people are not silent. Okay, so Ryan, I think your mic is on and it is broadcasting to the class. And then Matt, your mic is on too. So Ryan, could you turn off your mic or just mute your mic, please? Thank you. Oh, maybe not. It wasn't him. I still hear some kind of. Yeah, I think Ryan's mic is still on. Okay. Alrighty. It is time to start. It's 9:01. Um, yeah, so we do have bidirectional communication now. Because I found out that it doesn't matter whether you guys have voice chat capability. There's still an upper limit of 50 people who can join the screen share over Discord. I decided to turn it back on so that you guys can actually use your voice to ask questions if you want to. And I will still keep an eye on the text channel. You can see me looking to the side. That's me looking at the text channel to see if anyone is typing in the text channel. Alright, so I got a few people. Now we are too shy to talk. We are used to texting. Well, it's up to you. Mm. Um, if you want to, I can have your voice being recorded. If you do not want to, I can turn off that portion of my screen. So it's up to you guys. I mean, do you guys want your voice recorded? I mean, there won't be any images. I mean, it's just going to be a voice. Okay, we got I don't care, don't mind. I can always just repeat your question. I mean, that's fine too. So it's going to be my voice repeating your question. So I'm going to turn that off for now. Oh, okay, just curious. Okay. I just want to make sure that no one feels uncomfortable because in that case, I can always turn that off. All right, so what we'll do today is not to review the exam, and for a very good reason, because your exam has basically the same types of questions as the practice exam. I did not even bother to change it from subtraction to addition, which is usually what I do. Is I at least change a few things, like the number of unknown bits, change it from subtraction to addition and so on and so forth. So I did not do it not because I was lazy, okay, because it's actually just flipping a switch in the script that I use to generate the questions. I did not change it because I want to use this as an experiment, because I always change it and then and I never really quite know, whether if I keep the same format of the chain of the exam, would that make any difference, as opposed to changing it every single semester. So this is an experiment, and I think from your perspective, it is a good experiment because, unless you guys think, but I want you to keep changing all the questions so that, we are getting a brand spanking new test, with questions that we have never seen before. So if that is your preference, I am sorry that this particular exam disappointed you. But, on the other hand, I think most people prefer to go like, we would rather stick with something that is known, which is not something I can guarantee for exam 2 or the final exam. It's just that for exam 1, I decided to run this as an experiment. All right, so I'm keeping an eye on the text channel. If you have questions, go ahead and ask. But other than that, we're going to continue with our floating point number representation topic here, because I need to make sure that I cover enough material so that you can get started with your program or your homework assignment, after today's lecture. So there we go. And before people ask me, so is there a lab today? Technically speaking, yes, there is a lab today, except, the due date is not going to be at the end of the second lab session of today. It's just going to be in a week. I'll give you guys plenty of time to procrastinate. Yes, I did say that. Plenty of time to procrastinate, because that's what I usually see, in past semesters, is that people usually just some people, I shouldn't say the entire class, some people got it done like within the lab period, like within 3 hours they're done, and then some people decide to procrastinate until next, I would say next Wednesday or Tuesday, except my office hour is right after this class, right? And then my communication policy is the turnaround time is 24 hours. So people who do not bother to ask or to work on this thing until next Wednesday after the office hour may not get any response back until the following day after this assignment is due. So what am I telling you? I'm not telling you that I'm mean. I'm telling you to get started early. Okay, so get started early. You got a long weekend, so use that time to get started early, and hopefully you won't get into a situation where you need to find me and I'm not available. Okay, so there we go. All right, so what we're going to do today is to talk about the conversion from base 10 to base 2, both in terms of scientific notation. So to do this, I'm going to use my text editor to kind of illustrate the numbers. So that's going to be used for a little bit, and then we're going to change to the GDB, because GDB is going to be quite handy in this case. All right, so I'm going to go to Mousepad, which is my text editor. There we go. And then I will also talk a little bit about the programming environment, because you really got a few choices depending on how you want to do it, depending on how much you want to set up on your computer, whether you're using a Chromebook. Yes, you can actually use a Chromebook and get this assignment done. I mean, there's no need to actually have a proper PC in this case, which is going to be fun. It's going to be interesting. Okay, so I'm going to get started here. So I'm going to give you an example. Okay, 2.34 times 10 to the power of, let's see, we're working with negative exponent right now. So I'm going to say, negative 100 as the exponent of 10. Okay, so this notation is in base 10. It is basically just exactly 2.34 times 10 to the power of negative 100. Okay, so I want to convert this into the binary representation. Okay, so I'm not really too concerned about, how many bits do we have in the mantissa, how many bits do we have, for the exponent of 2, and so on. I just want to convert everything into base 2. Okay, so one thing we want to keep in mind is the value being represented is always something like the mantissa. So when I use the term mantissa, which is abbreviated to M in this case, is really kind of not exactly the definition of mantissa. It really is just a quantity that we multiply to the following. So the following would include something like 10 to the power of exp10. So in this particular context, because we're working with actual values, this is no longer talking about exclusive OR, it is to the power of. Okay, so in the context of today's lecture, when I use the caret operator, it means to the power of instead of bitwise exclusive OR. And bitwise exclusive OR has no application related to what we are trying to do here. So there's no need to say, oh, but it's going to be confusing because we need both. No, we don't need exclusive OR for this particular discussion. So in addition to this, we're going to say we also want to have a portion of the value expressed by a multiplication to 2 to the power of exp2. So exp2 is really just a variable, or name that I use for the exponent of 2, and then exp10. Let's abbreviate these two to just e2 and e10, so I don't have to type the xp. Okay, so are there any questions at this point about how a value is represented at this point? It has three components. It has M, which is what we usually call the mantissa, except this particular mantissa is not going to be normalized. And then it has one component, which is a power of 10, and E10 is guaranteed to be an integer, so we are talking about an integral power of 10. And then we have the last component, which is a power of 2, an integral power of 2. So are we good so far? This is how we will express a particular value, by manipulating M, E10, and E2. All right, so that's good. Thank you. All right. So I think somebody's mic is still on because I can hear the echoing of the notification. So if that is your mic, please turn it off or mute your mic until you want to actually say something. Thank you. All right. All right, so we're going to go back to this example here, okay, and say, okay, but how do we express that? So the value in this case is 2.34, okay, 2.34, that's the M initially, times 10 to the power of negative 100, and then somebody's going to say, but what about E2? We never really express anything about E2. Well, that's fine. We'll just call it 0 then, right? So this is the value that we want to represent. The first thing is I want your entire program, okay? Let me just emphasize that I want your entire program to only make use of integer math. You cannot use exponent, you cannot use power, you cannot use log, you cannot use anything other than the native operators that C and C++ has defined for unsigned 64-bit integers. Okay, so that's the limitation. You cannot use any of the math functions that natively use double or float. All right, so now what we want to do is to say, we eventually, okay, blah, 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 eventually we want to express this as some kind of M times 10 to the power of 0 times 2 to the power of some E2. But we want this, okay? We want to basically make E2 and M to represent the original value when the exponent of 10 gets down to 0. And we want to make it as close as possible, okay? That is a very important point to emphasize, that we just want it to be as close as possible, because most of the time it's not possible to be exact, okay? We just want it to be as close as possible. So does everybody understand what we are trying to do here? We start off with a representation that looks like this, and we want to end up with a representation that looks like this. We're trying to get rid of the exponent of 10, but we have the flexibility to play with the mantissa and also the exponent of 2, so that we end up with a value that is as close as possible to the original one. Okay, so I want to give people a little bit of time to ask questions if they have any questions about what we are trying to accomplish here. And that we have done already. Okay, we have done a little bit of this in the lecture before exam 1. I gave you some very simple examples of how to get this done. But we want to be able to do this with some kind of insane values, because 2.34 times 10 to the power of times 10 to the power of 100 is a very, very, very small number. I should say it's very, very close to 0. So, the usual way of doing things by hand doesn't work here anymore. All right, so let me re-emphasize here, okay? Use integer operators only. Okay, so for this entire operation, we only want to use integer operators. Now, some people may ask, but why? This is just making the assignment much harder than it needs to be. Well, it's because, there are two reasons. One is there are some architectures, processor architectures, where there are no hardware floating point number units. And for those particular architectures, which would include some of all of the Arduinos and some of the Raspberry Pis, using the double math is going to be very time consuming, and we don't want to waste time unnecessarily. So Okay, so we got some questions here. So, are we going to need to write your own exponent function? No, we don't need the exponent function. Okay, so that's the whole point. Is we don't need the exponent function. We don't need log. So hopefully by the end of today's lecture, we'll understand how to do all this using loops, conditional statements, and so on and so forth. And yeah, so Jonathan is correct. We're going to use some loops. Okay, so you can use a for loop, you can use a while loop. They're basically equivalent stuff. Depending on how you look at the initialization, the post operation. So, so there we go. All right. So now we're going to talk about the conversion process. So in the conversion process, okay, for simple stuff, okay, it's not really too bad. So I'm gonna use this as a notation of going like, okay, let's look at a very simple example. Okay, so this time we're looking at let's see, let's try 3.75 times 10 to the power of -1. So this is the value that we want to represent in base 2. Okay, so how are we going to do this? This one turns out to be like super duper easy, because the first thing we do is, but Tag, you did some. You mentioned that we cannot represent, we cannot use double, we cannot use float. Okay. Okay, so let me just re-emphasize what that means. Do not use anything that requires the float type. Okay, float or double types. Okay, so no variables of these two types, no functions of these two types, whether it is supplied by the C library or whether it's something that you implement. I don't want to see anything, okay, that has float or double in it. So right away we have a problem. It's like, but what about this? What are we going to do with this? Well, I'm giving you some code to begin with. So my code will automatically convert this so that the mantissa would become 375. And I would also manipulate this entire thing so that the power of 10 is no longer -1. And I'm going to ask you guys, what do you think is going to be the new power of 10 in this case? We want to maintain the same value? Nope, it's not 0. It depends on how many times we are going to move the decimal point to the right hand side so that 3.75 becomes 375.
Is it 1?
No. Think about it. Think about it, okay, people? Think about it. 3.75 is less than 10 to begin with, and when we multiply that to 10 to the power of -1, it becomes less than 1, right? So if I want to get an exponent here so that the value is still less than 1, what do we need? Which direction should we go? Positive or negative in terms of the power of 10? Negative, that's right. Okay, so this is the kind of way to think about it, is really to look at the constraints. Okay, the value that we are trying to represent is less than 1 to begin with. So when I change it to become 375 times something, that something got to be pretty small, smaller than 0.1. So it's just a matter of figuring out how many times we have to decrement or decrease the power of 10. And Matty is correct, Ivan is correct, Kyle is correct, John is correct, Colton is correct, Jonathan is correct, and it is going in the opposite direction. So it would be -3 because we have to move the decimal point twice, and each time we move the decimal point, we have to change the exponent of 10 to make up for the change of the value of the mantissa, so we end up representing exactly the same value. Not 375, but the product between 375 and 10 to the power of what we know as E10. That has to, this particular product needs to be the same as this particular product here, because we have an equality here. Yes, that would be 0.375. That is correct, Maddie. All right, so my program does this part already. Okay, so that's why you don't have to worry about, but how do we represent 3.75? That's done already. Okay, so now we look at this quantity here, we look at this thing here, and we ask, Okay, so how do we convert this? Let me just copy this onto a new line, like so. So eventually we want to express this as some kind of m times 2 to the power of some e2 value here. So we need to solve for this e2, we need to solve for the m, and we want to make it as close as possible, and in this case it is entirely possible to be just exact. Okay, all right, so how do we do this? What do you think? Any suggestions? All right, so the next question. Okay, um, let me give you an idea. Okay, so we basically want to bump up um, this -3 to -2 first. Okay, and how do we do that? Okay, so we want to say, how do we change the power of 10 so it becomes -2 instead of -3? And some people would say, oh, we just have to change 375 to 337.5. Then we can change this -3 to a -2. Well, that is not a very good idea, because that means once again we need a floating point number representation, because 37.5 is not an integer. Okay, so we cannot go that route. Darn it, what are we going to do? So let me introduce a method. Okay, so what we do is we make the mantissa really large, and then we'll be able to make adjustments to it. Okay, so let me check the channel. We multiply by 2 and then increase e2. Well, if we multiply by 2, we actually have to decrease the exponent of 2. So but it's a right move. Okay, it's in the right direction. So what we'll do is we're going to say, okay, let's double the mantissa. So when we double the mantissa, I'm just going to do the calculation on the other side. It becomes 750. So this becomes the same as 750. And I'm still not changing anything to the power of 10, but this time I have to adjust because the mantissa just doubled, and as a result, now I need to compensate for the doubling of the mantissa by introducing an exponent of -1 for the base of 2. Okay, so so now e2 actually becomes useful because I need to put a -1 here to compensate for the 750. Are we still doing okay so far with the equivalency between the product here and the product over here? Are we still doing okay so far with that part, with the math? Okay, so we are still good with the math. Very good. Okay, so in this case, in this very specific case, okay, some people will look at this and go like, Tech, I think we can divide the mantissa now by 10 and therefore increase the exponent of 10 by 1 at this point. And you would be 100% correct. So that would be easy to do. We just say, hey, this is 75 times 10 to the power of -2 times 2 to the power of -1. Two times e2 to the power of e2 is 2 times okay, so I can see where the confusion is, but the scientific notation ends here. Okay, so the meaning of e being times 10 to the power of ends here. So for the rest, e10 is a variable, e2 is a variable. So e10 and e2 are their own variables at this point. All right. So we look at this representation, and then we go like, now we're kind of stuck again, because if we divide 75 by 10, it becomes 7.5, and we don't want to I mean, you can truncate 7.5 to 7, but that means you're losing a lot of precision, and we don't want to do that, right? So we look at this and go like, let's see if we can do that trick again. Let's multiply this thing by 2 again. So this becomes 150 times 10 to the power of -2, but because we just multiplied the mantissa by 2, so now we have to decrease the exponent of 2 by 1 to compensate for that. So let me check the text messages here. So to get 75, you express 1 of the 10 to the power of -1 to the Uh, okay, so when we divide the mantissa by 10, we have to bump the exponent of 10 up by 1. That's because we want all of these to be equalities. We're preserving the value being represented, but we just want to kind of manipulate this component. We want to be able to and this component in the process. Next one in the text channel is we just do what we did until 10 has a power of 0. That is correct. So Richard, you are absolutely correct that that is our strategy of how to get this done. And Matty says they are a variable in that you could just use something like x, but we are using E10 and E2 to give them unique names. That is correct. Yes, there's going to be, it's repetitive, right? This whole thing is kind of repetitive. So we look at this and go like, that is nice. 150 is a multiple of 10, so we can now change it to 15. But when we divide the mantissa by 10, we have to bump up the power of 10 by 1. So now it is one step closer, almost there, right? So now we look at 15 and go like, darn it, if I divide 15 by 10, we get something that is not an integer. So now we go like, okay, so what did we do? We multiply 15 by 10, by 2, sorry. We multiply 15 by 2, so it becomes 30. But because we multiply the mantissa by 2, we have to remember to bump down the exponent of 2 by 1. So it now becomes 2 to the power of -3. And now we can say, hey, this is kind of nice because 30 is divisible by 10. So now it becomes just 3 times 10 to the power of 0, because we have to bump up the exponent of 10 in the process, times 2 to the power of -3. So as far as your assignment is done, we don't have to convert everything into the actual double representation, because the last part of the process is pretty simple. Okay, this is not really quite the end of the entire conversion process as far as your homework assignment is concerned, because it's going to be described in the assignment itself. But this illustrates the idea. Okay, it illustrates the idea that you can play with the power of 2, and you can play with division by 10 with the mantissa in the process of trying to get the initial power of 10 all the way to 0. Okay, so this is the purpose of this example, is to illustrate the general strategy of how we can move the exponent of 10 gradually up until we get to 10. And your assignment only has to do with an initial negative power of 10. So the positive power of 10 is going to be the next homework assignment, not this one. All right, so let me check the messages. We got a few people typing, and then we'll talk about the more extreme case of what if we're dealing with a power of 10 that is 100, negative 100, because that's going to be troublesome. Okay. Excellent. I'm glad to hear people saying that this is clicking. We are the positive power is going to be opposite strategy, so that's for the next lecture. So it will be manipulation via division by 10 or multiplication by 2. It's both. Okay, it is both, because you can see how we actually it is division by 10 and also multiplication by 2. That is correct, but we have to do both. So the question is, when do we stop, right? And what if the negative exponent is really, really horrendous, like negative 100? What do we do in those cases? If your modulus is over 1, you multiply by 2. If not, divide by 10. Not quite. Okay, so we're going to get to that. So from these questions, I can kind of tell that, maybe some people have not read the module, like a little ahead of the class, ahead of the lecture. So once again, that is important, because, if you had done that, the material will be much easier to absorb in the lecture. All right, so let's go ahead and look at the more extreme example, which is the one that we are trying to deal with here, this particular example. Okay. So we're going to take this thing here, and then we'll paste it over here. And then we ask the question of, what are we going to do with this, right? Because we eventually want to be able to, actually I take it back here. This example, cannot be done using this particular approach because we are now re-expressing this as 234 times 10 to the power of negative 102. It's getting worse, right? It's not getting any better. Times 2 to the power of 0. So what are we going to do in this case to solve the problem? We can't really just use this approach anymore. Okay, and we want to be able to do division by 10 so that we can every time we do a division by 10 with the mantissa, we can bump up this portion by 1. Okay, so that's kind of the objective. But at this point, you can see that no matter how I multiply this amount by 2, it will never be a multiple of 10, right? I just chose this number here because it just works out very nicely with the example that we were using before. This one doesn't quite work out as nicely, so I'll give you a few steps, and then we'll go ahead and switch to my GDB because I got some scripts set up so that I don't have to do all the math with my I don't have to do all the manual math. Okay, so we're going to look at this and go like, okay, so we'll go ahead and multiply 234 by 2, which is 468 times 10 to the power of negative 102 times 2 to the power of negative 1, right? It's still representing the same value, but I don't see the mantissa being a multiple of 10, so I kind of hesitate to divide it by 10. So at this point, we can multiply again, exactly. But no matter how many times you multiply, it will never, ever be a multiple of 10, right? So now we want to talk about the business of errors, okay? So the business of error is, if you divide 234 by 10, what is the error margin of error? Now, if you were to bump up your 468 a few times, and let's double it again. Okay, I'm using my little calculator on the side to do this calculation. So when you multiply by 2 again, it becomes 936 times 10 to the power of negative 102 times 2 to the power of negative 2. And if you multiply that by 2 again, okay, becomes 1872. So I'm just going to do this a few times to illustrate the issue of error margins, or the margin of errors. So this becomes 2 to the power of negative 3, and we'll do it one more time. Okay, we'll do it one more time, and that should be enough to compare to the original mantissa when we divide it by 10 and take the floor of that. So we will bump this up one more time, becomes 3,744. So 3,744 times 10 to the power of negative 102 times 2 to the power of negative 3. Okay, so we'll stop here, okay, because I want to see if I were to divide 234 by 10, what would be the margin of error? How bad is the error? So we take the floor because integer division is truncating the decimal part. So we're going to take the floor of 234 divided by 10, and then we'll subtract the actual value of 234 divided by 10, which is just 23.4. And then we'll take this, because this is the error, and it will take this entire error and divide it by the original, by the proper amount, which is 234 divided by 10, and then we get the error rate in this case. So this particular error is going to be, okay, let's see, the floor of, so it'd be 23 minus 23.4, the whole thing divided by 23.4, and okay, I'm going to use a spreadsheet to work this out. Where's my spreadsheet? Under Office, and it's under Calc. There we go. And we don't need to. Alright, so here's my spreadsheet, and we'll do the calculation. Now, the nice thing about a spreadsheet is if you structure in a particular way, so I'm going to structure in a particular way. So this is going to be the previous cell times 2. So this way I can actually, the previous cell times 2. There we go. So this way I can actually work out a whole bunch of numbers at the same time. And then we're going to look at the error rate over here. So the error rate is expressed exactly like this, except I'm not going to use 234. I can refer to the cell in column A. So everywhere you see 234 in the spreadsheet, I can replace it with A1 in this case. So this way the error can be calculated quite easily. So we have the floor of this thing divided by 10 minus the actual amount of this thing divided by 10, and then the whole thing, oh, that's not a, yeah, that's a minus, and then the whole thing divided by the actual value of, okay, I think we need one more close, divided by just this thing divided by 10. And so basically what you're seeing here is the error, and I just have to drag it to see how the error changes as we change the number in column A. So what are you observing? Let me just change column B to use a scientific notation, so this way it's easier to look at the quantity. So we want to go to format, number, format, and we'll change it to scientific notation. There we go. Yeah, it keeps getting smaller and smaller. Okay, so when you look at this and go like, hey, I like this, okay, because we like margins of error that are smaller and smaller. Now the question is, how far can we push this, right? How far can we extend this whole thing so that we get the minimum possible error when we divide it by 10? So what do you think? When can we say, Tack, I think we cannot do this any further? Remember, you can only use integers in this entire program. So what do you think is the boundary? When do you say, okay, that's I think that's enough. If we double again, we cannot store that anymore. Nope. It's not 2 billion because 2 billion is only for 32-bit numbers. Okay, we can work with 64-bit numbers. So 64-bit, turns out to be, I mean, there's a certain maximum. So this is a good time to mention that would not be true. No. All right. I think you guys are forgetting the discussion of how do we find the maximum value of an unsigned representation given a the bit width of the integer. We talked about that. Yes, we did talk about it. Yes. All right. Well, let's go back to that, right? Okay. Given n bits, okay, the largest unsigned value is 2 to the power of n, the whole thing, minus 1. So in this case, with a 64-bit number, it's going to be 2 to the power of 64, the whole thing, and then minus 1. Subtract 1 from that. Okay, which is a pretty big number. Okay, it is a pretty big number, but nonetheless, it is a number. It is finite. Okay, we can only push this approach. Let me put the spreadsheet back in your view. We can only push this so far until we can no longer double it, because if we double again, it's gonna be out of range. Okay, we can no longer represent the result of doubling it anymore using only 64 bits. All right, so how do we get to this particular value? Okay, because remember, you cannot use to the power of. Okay, there's no such thing as to the power of. So some of you have already thought of it using bit shifting, which is great. Okay, so you can say this whole thing is the same thing as 1, which is 2 to the power of 0, shifted 64 times to that side, and then we just have to subtract 1 from it. Except this approach is not going to work, because this quantity itself cannot be represented using 64 bits, because this quantity would be 1 followed by 64 zeros after that in binary, so it's not going to work. So what are you going to do? And somebody's going to remember the number wheel, right? Remember the number wheel thing? As it turns out, -1 and the largest integer given given n number of bits, they share the same representation. So you can actually say, oh, so we can do something like this. Except if you do something like this, the compiler is going to say, oh, you mean -1 as a value. So in order to coerce the compiler to think that this is not -1 that you're talking about, you just have to say, okay, hey compiler, I know what I'm doing, so why don't you just look at the representation of -1 and interpret it as a 64-bit unsigned number instead. Okay, so that is going to give you the same thing. So I know some of you do not believe it, so I'm going to put GDB up here so that you can actually see it. So if you say print -1, it is just -1. But if you say print uin64_t and typecast it to typecast the representation of -1 into uin64_t, then it gives you, oh darn it, that's because I did not run the program and the type has not been defined yet. Sorry about that. That doesn't work. We can GDB. What is the name? Define X. There we go. Okay. So I have to give it a program before I can try that trick. So let's see if that works here. 64_t. The whole thing. All right, that works, right? I mean, so this is one way to find out what is the largest value you can represent as a 64-bit unsigned integer. So that's one way to do it, but the proper way to do it, just because you can do it this way doesn't mean it's the proper way to do it. So the proper way to do it is to look up, okay, on the internet, look up stdint, .h, and the first link will link to it. And what we want to do is to find the largest, the representation of the largest 64-bit unsigned integer. So I think you guys can read through all of this stuff here, but I think if you are proficient with searching, you're going to say, looks like we're going to find the maximum value of something. So let's look for max here. So there we go. We have greatest with integer type. And then we're gonna have, keep searching, there we go. So this is what we are going to use to find out the macro that is representing the maximum value of exact width, which is 64-bit in this case, unsigned integer type. So anyone who is going to use this as a macro to represent the largest value of a 64-bit unsigned integer is gonna get a compiler error, okay? Because there is a reason why this n here is italic. Can someone guess why n is italicized? N is a placeholder of the number of bits, exactly. And in our case, it's going to be 64. So if you just say uint, all uppercase, 64_max, and you pound include stdint.h, it will give you the largest value that you can represent using a 64-bit unsigned integer. Isn't that cool? Kinda? Yep, just like that. Richard. Very good. Okay, so excellent. Alright, so getting back to our example here. So getting back to the spreadsheet first. Okay, so getting back to the spreadsheet. So this means we can keep going like this until we hit that limit. Okay, and that limit is what? I think it's 1.8. Okay, we'll keep going and keep going. Okay, I think we have a few more times, and now we're getting pretty close. I believe this one is too much already, okay? And the amount of error is really small. I mean, it's basically saying, there's still an error, okay? And the reason why it's not reporting an error is because in the spreadsheet, it is actually using a double representation all the time, and we don't have enough precision in a double to represent, the difference between the two, so it would basically quote unquote crap out a little bit too early and report that there's no actual error when there is actual error here. But the point is you can only double it for so long, okay? So now I'm going to give you, the basic approach here. Okay. And I'm not going to deal with the changing of the exponent. I'm just going to focus on one thing, which is how far can we double 234 until we run out of space to double it again. Okay, so we start with set var x equals to 234. I can show you the. Oh, okay, I have to run it first. There we go. No. Oh, okay. I think I know why this is not working. Source start.gdb. Okay, so now we are going to set var x equals to 234, and I have defined some macros here. Okay, so I'm gonna source handy. Yeah, we're gonna redefine those too. That's fine. Okay, so I have defined some macros in GDB just so that I don't have to type and check the conditions all day long. So whenever I do a CMP LSH2, it's going to left shift or multiply x by 2, and it will also compare x with the largest value we can represent in base uh, in the 64-bit unsigned integer, and and if it is still less than, it will double it. I should say the opposite. It will first check whether we can still double it or not. If it can double, it will double it. There we go. I don't understand what you mean when you call something a macro. A macro is basically just you can look at it as a function, so it is just doing a few things for me that I don't have to do it. Okay, so this is in hexadecimal representation. It doesn't really matter whether it's hexadecimal or not, because what does matter is it has room to double. So we're gonna double again, double again, double again, double again, double again. So alright, so we are going to get to a point where it can no longer double, and it will stop doubling at that point. So we're going to go keep going, 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 and now it says it's maxed out. So at this point of time, x is already maxed out, which means if I double it one more time, we won't be able to represent the product between x and 2 because it will require more than 64 bits to represent. So now we can do a division by 10, but we don't want to just do a division by 10 because just doing a division by 10 and then take the floor has some other issues. But before we continue, let's take row. I did not forget about row taking today, so let me find a window that I have set up already. Give me a moment here. Nope, it's not that one. Oh, it is that one. Okay, just on a different tab. Alright, so I'm going to pull this into your view and show you the answer first. And this one is really boring. It's hardly surprising. The answer is exponent. I'm going to copy and paste it into the text channel. There we go. Just copy and paste it. Once I release the activity, it is now released. So copy and paste it from the text channel. And that's row taking for today. And you have until 9:57 to do it. So that's plenty of time. Even if people decide, I kind of need to run to the bathroom, that's still plenty of time. Yeah, cool. All right. I'm not sure what is showing up or not showing up. Oh, okay. All right. So I think most people are is not showing. Yeah, I had to scroll up. Sorry. I moved it. well, I should say I didn't move it. I just kind of pick one of the unused one. It's right under floating point number representation. So for people who want to find it, it's right under floating point number representation in Canvas. All right, cool, cool. Yeah, sometimes I don't do things in a sorted way. All right, so I think most people are done with that, and now we can get back to this business over here. So, division by 10 sounds pretty easy, right? Except there's a problem because even though we are using a huge number and we divide it by 10, which means the error is going to be pretty small, there's still a problem. Okay, so let me illustrate what the problem is. Okay, so if I compare the floor of some gigantic value, okay, say x divided by 10, x is really huge, okay, and I subtract the actual value of x divided by 10 from it, what is the sign of this particular value? Is it going to be, is it going to be 0? No, we don't. It's not going to be 0 most of the time because we know x can be a value where when you divide x by 10, there's a fractional part. The question is, what is the sign of this particular difference? Is it going to be flipping between positive and negative depending on x, or do you think it's going to be sticking on one side of the number line? It's always going to be negative. Exactly, because when you take the floor of something, assuming x is non-negative, obviously. So assuming x is non-negative, when you take the floor of something, the floor of x divided by 10, that's always going to be smaller than or equal to x divided by 10 itself, because it's always rounding down. Exactly. So math has the best explanation because it's always quote unquote rounding down. Okay, so to give you an example, and this is why one of the earlier labs has a question like this. So when you look at x being 14, okay, then you have floor of 14 divided by 10 minus 14 divided by 10, which is negative, right? So when you look at the floor of 19 divided by 10, okay, subtract 19 divided by 10 from it, it is also less than 0. The only time it is actually 0 is when you have a multiple of 10 to start with. So the only time it is not going to be negative is when you try to take the floor of, say, 200 divided by 10 minus 200 divided by 10, then you get a 0. So what this is showing you is if you just take the floor of a division, which is basically what integer division is. Okay, so when you have unsigned integer division, it's basically equivalent to taking the floor of the actual result of the division. But the problem is now it has a bias. Okay, so this has a negative bias, which means what you're getting as a result after division is always smaller than what it is supposed to be, which is problematic, okay? Because even though the error is really, really small, it is still always leaning in one direction. So when you repeat those operations a few times, the all these tiny little errors in the same direction, they all add up to become a problem. So we don't really mind errors when they're small, but we do mind that if they're all in the same direction. So how do we fix this problem? So the way we fix this problem is, and Matty is typing something. I'm going to wait until she's done typing because she might be giving us the solution to this problem. Oh, the stream is getting laggy. Uh-oh. Is that the same for everybody else? Okay. Alright, so it could be a localized problem for Maddie. Okay. As long as the YouTube stream is not impacted, you can always go back and revisit a part of it. There's not much I can do to affect how things would turn out on the other side. because I think I'm using the lowest bandwidth requirement already when I'm encoding my screen capture in Discord. All right, sorry to hear about that. Okay, so the solution to this problem is instead of flooring, we're going to do rounding. Okay, so exactly. This is why we had that lab and have those questions. So when we look at rounding, okay, so I'm going to use a few examples here before we generalize of how we do actual rounding. So the round of 1.1 is 1. The round of 2.5 or 2.6 is 3, and so on. So what we found out, okay, in the discussion is taking the round of something. Okay, so if I give you any value, okay, an irrational number as x, okay, the round of x is really the same thing as the floor of x plus 0.5. That turns out to be true for all non-negative values of x, and we are only dealing with unsigned integers here, so this is going to be okay. So, if you apply this, okay, figure out, let's check it out, right? If you don't believe me, so this is the floor of 2.6 plus 0.5, which is the floor of 3.1, which is 3. Okay, so that does work out. What about this one? This is the floor of 1.1 plus 0.5, which is the floor of 1.6, which is also 1. That works out too. So this is really kind of useful because now we can use the floor of something to implement the round of something, because round normally is a double function and you're not supposed to use a double function. Okay, but we still have a problem here. But hey, this 0.5 here, isn't this a problem? Because how do we represent 0.5 if we cannot use integers? Well, the nice thing is the only time we need to use round is when we divide something by either 10 or 2. So in this case, it's only division by 10. So when we say we need to take the round of some value divided by 10, because it's always in the case of a division that we need to round something. So now we look at this and go like, okay, fine, we established earlier that this is the same thing as x divided by 10 plus 0.5. And how are we going to get rid of the 0.5? Well, how about we do it like this? X plus 5, the whole thing divided by 10. Now, if someone is asking me, I'm not sure that this expression is the same as this expression, I am going to refer that person to remedial math classes, because this is algebra. Okay, all we are doing is we are, changing the 0.5 to 5 divided by 10, and because it becomes 5 divided by 10, it has a common denominator with x divided by 10, and now they can be on the same side as the numerator, and because they have the common denominator. So that's arithmetic. Okay, so I'm not going to further explain this math over here. However, on the other hand, when you look at this thing here, hey, we don't need no stinking double or floating point representation. Everything is our integer, right? X plus 5 is going to be an integral amount. 10 is integral, and the division itself goes like, but this is not integral. It is if we are going to take the floor of the division, because when you take the floor of two integers dividing, one integer being divided by the other integer, then you basically just have integral division. So now we have just converted all of the operations to integer math. And Jonathan is asking, are we allowed to use floor for the assignment? The answer is no, you don't need it. Because if x is unsigned, 5 is unsigned, and 10 is unsigned, doing just this is the same thing as taking the floor of the same thing. Because in integer math, this is integer division. So integer division is automatically taking the floor of the division already. So you don't need to use floor at all. So we basically avoid the use of everything that needs double. Yep, exactly. So Matt is correct. It always dropped the fractional side. And if people do not believe me, because there's no reason to believe me, right? So you print 14 divided by 10 is just 1. Okay, and if you say, but 14 is not necessarily an unsigned integer, well, let's typecast it, right? Typecast both to unsigned. Now I only use unsigned here instead of uin64 underscore 10 underscore 64 uin64 underscore t. Sorry, that's it. Because 14 and 10 are pretty easy to represent. We don't need 64 bits to represent 14 or 10. So it still comes out as 1. Okay, and that's because the integer division operator is guaranteed to only return the floor of the division. So it's doing both at the same time. Isn't that nice? So what do we do with x now? Okay, now remember, of all of these operations, I'm totally neglecting what I need to do with exp2, or the exponent of 2, but I think you got that from the earlier discussion already. So I'm just focusing on the mantissa itself. So right now we go like, well, since we cannot multiply this x by 2 anymore, let's go ahead. This is the last chance. Okay, we have to divide it by 10 at this point, but we don't want to just divide it by 10. We want to do the rounding thing. So now we say set var x equals 2. Let's add 5 to x first and then divide it by 10. And the plus 5 is exactly for this purpose here, okay, because we want to do rounding and instead of just flooring, but in order to do rounding, we just have to add 5 first to the number that we are dividing by 10. Then it becomes the rounded version of the whole thing. So now we have a new value of x. Let's check out x. So x is now this particular value. If you want to look at it in hexadecimal, it is this particular value. What do we do next? Okay, because at this point, whenever we divide x by 10, I know we have to add 5 first, but the add 5 is only doing the rounding part. So effectively speaking, we are just dividing x by 10, but in a rounded, fashion. So what do we do when we divide x by 10? Remember, x is representing the mantissa. So whenever we divide the mantissa by 10, we have to bump the exponent of 10 by 1. So in this case, it would have bumped it up from negative 102 to, guess what, negative 101. So we got one tiny step closer to where it is supposed to go. Okay? Then the next question is, then what do we do? Well, guess what we're going to do? We're going to double x again and again and again until we cannot double anymore. Divide it by 10 in a rounded way, and then we bump it up and bump it up, multiply, doubling, and then divide it by 10, doubling, divided by 10, until the exponent of 10 becomes 0. So I can use this macro to do it a few more times. Okay, so now it doubles to 5D99998, double again, go like, nope, we cannot double anymore, because if we double this, it's going to run out of bits to represent in the 64-bit representation. So what we do is we set var x equals to x plus 5, the whole thing divided by 10. And remember, every time we double, you have to adjust the exponent of 2. Every time we divide it by 10, you have to adjust the exponent of 10. So now let's print what is x at this point. So this is the amount of x. So what do we do now? Well, at this point, the exponent of 10 should be adjusted to the negative 100, because we have divided the mantissa by 10 twice at this point. So it would go from negative 102 to negative 100 at this point. So we just have to keep doing this 100 more times, and we'll be done. Easy peasy, right? Because guess what? You're not going to do this by hand. You're going to set up some loops, and you're going to have a C program to do all of this. So all you have to do is to understand the logic of doing this. And before someone asks me, can you show us what is CMP LSH2? The answer is no, because showing you that basically just gives away a good portion of the answer. Okay, but I can tell you what it does. Okay. What it does is it looks at the current value of x, which is your mantissa, and determine whether we can double it or not. If it cannot be doubled, then it will give you this message here. If it cannot be doubled, it would just say that it's already maxed out. If it does have room to double, then it will actually just double the amount of x and then show you the new value of x. So no, I am not going to show you the macro of CMP2LSH2, but I just told you what it does. Okay. All right. So now the next question is, how do we know whether we can double x or not? Right? So let's try to answer that question. Okay, so the question is, how do we know whether x can be doubled again? That is the question. So the idea is, if I double x and it is exceeding what a now this is no longer entirely true, okay, because in the math, okay, remember we have to add 5 to x first. So this is not what we are really comparing it to, because we have to remember that we might potentially add 5 to x first. So that means we have to adjust for that. So that means, if we let me see. Yeah, so we have to potentially say that we might add 5 to x first. So we are comparing this amount, and if it is greater than, okay, equal to is not a problem. If it is greater than u in 64 underscore max, then we have a problem. Okay, if this is the case, do not double. Okay, so if blah blah blah, do not double x. Is that okay? Does everybody understand what I'm representing here? And x is just the mantissa, so might as well change it to m. Okay. But this math has a problem, because there's no 64-bit unsigned value that can ever be greater than u in 64 underscore max. Why is that the case? In a way, it is a very stupid question, but in a very obscure way. So that makes it a stupid but obscure question. So I'm going to give, okay, so several people are typing. I'm going to, exactly, because this is the maximum value already. It is called the maximum value for a reason, because no other 64-bit value or unsigned 64-bit value can ever exceed this amount. So that means this is not a good way to do the comparison. All right? Exactly. So Colton is correct, Matt is correct, and Jonathan is correct as well. So all of you are correct about this assessment. This is not a good way to do the comparison. Now, if you're in a math class asking a math professor, the math professor will say, I don't see a problem with this. I mean, this is fine. But this is a programming class. So when we talk about integers, we are not talking about integers in a math sense where there's no upper limit. When we talk about integers, there's a minimum and there's always a maximum of what you can represent in an integer. So because of that problem, we now have to use algebra so that this thing will still work out. So when we use algebra, we can now say, okay, we'll move the plus 5 to the other side. U in 64 underscore max minus 5. And then after that, we can divide both sides by 2, right? So we have m on this side, and then we have u in 64 underscore max minus 5, the whole thing divided by 2. Now it looks better, right? Because this amount certainly can be represented in 64-bit as an unsigned integer, and this one certainly can be done like that too. M is already a unsigned 64-bit integer, so this is a nice way to do it. Alright, so Jonathan typed it would be greater than the possible max of an unsigned integer with 64 bits. Yep, that is correct. Alright, so I just gave you guys, I just solved a puzzle for your homework assignment. And from this, thing here, I'll do it a few more times, just so that you can get a sense of, how to structure your control structure, how to structure your statements and whatnot. Okay, so we have just divided x by, or the mantissa by 10 again, which means it's time to double, right? How many times? blah, blah. How many times do we need to double? It kind of depends. Okay, I'm looking at the time because I need a few minutes still to help you guys set up where you can do the C programming and stuff like that. But I do want to make this point. How many times you have to double before you can divide the mantissa by 10 again? Depends. Okay, it sometimes it's 3 times, sometimes it's 4 times. Why is it between 3 and 4? It's because 10 as a value is between 2 to the power of 3, which is 8, and 2 to the power of 4, which is 16. So that's why, depending on your actual x, sometimes you need to double it 3 times to kind of max out again. Sometimes you have to double it 4 times before it's maxed out again. So it's best really just to keep doubling until you cannot double anymore. Okay, so instead of trying to predetermine how many times you can double, just keep doubling, doubling, doubling until you cannot double anymore. All right. So this is a good portion of the logic that you have to deal with. Now we're going to move on to where you're going to write this program. So if you have a C compiler installed on your PC, especially if it's GCC, you can go ahead and use it. So let me point to the assignment or the lab. I call it a lab. It's really more like an assignment. So let me publish it first so that you can so that you have access to it already, because I think that makes the discussion a little bit easier if you can see the description. So I'm gonna make this due next Thursday. So you have 1 week to work on it. So next Thursday is October 7th. Wow, okay. So October 7th, and the time is going to be 9 a.m. And same thing over here. October 7th, 9 a.m. And I'm going to have it published. Okay, so in the text channel, do you have any restrictions on C versus C++ as long as we use integer operations? No, I do not have any restrictions as to whether you can use C or C++, but the restriction is still you cannot use any double or float type of operations. You can use anything. So here's the good part about the homework assignment. You have a flexibility. Okay, you have plenty of flexibility of how to do this. All right. So there's a source. There's a zip file. The zip file, it will unzip to a folder, and in the folder I have code blocks already set up as a project. So that's one way to do it. The other way to do it is to go to online GDB, which is a website, and in that case you cannot use multiple source files, so you will have to rely on the single source file. So this is a download link, so is that one. It is also a download link. So I give you an idea of what a single source file looks like in this case and how to run it. Okay, I'm going to show you how to run it in both cases. So let me first download the double1.zip. Okay, I'm going to save it to my temp folder. Okay, and I'm also going to download the single source file, and also going to the temp folder right there. Okay, now for those of you who already have an IDE set up, whether it's VS Code or CodeBlocks or some other IDE, you can go ahead and use whatever IDE you have. You just have to make sure that you put all the source files into your project properly. And there's one more thing, which I will show you right now. Let's see, command line. There we go. Alright, so I'm going to open a new tab in my command line, go to the temp folder, unzip double1.zip, which unzips into its own folder. So in this folder, if you use CodeBlocks, it has a project file set up already, which is the double1.cpp. So if you have CodeBlocks already installed, you can just type CodeBlocks and then double1.cpp. I'm not sure whether that's going to work or not. I think I might have used the wrong name. Yep, I used the wrong name. Sorry. Nope, do not close this. Alright, so code blocks is the one that I want to close because I used the wrong name. Oh, it's complaining the project file does not exist. There we go. Close it again. Okay, because I just had an operator error here. Okay, so let's try this one more time, but this time we use double one. There we go. Alright, so this is the project as it is set up in code blocks. Oh, if you want to go for dark mode, you can install plugins in Firefox. I can switch to dark mode. Okay, I know I'm digressing here, but since Maddie asked, I'm going to get to is it extensions? Nope. Okay, where did I put that? I think it's under settings, under extensions and themes. Okay, put it into a separate tab, which is annoying. Alright, so this is the tab. If you use dark reader, you can turn anything into dark mode. Oh, I just disabled it. Oh, okay, it's how do I turn it on? Anyway, there are plugins you can use, to turn it into dark mode. Yes, I understand the necessity of dark mode. People compare developers to vampires. So when we look at something like this, you can quote me, it burns. It burns my eyes. Anyway, so the important part here is you have to set up, if you have to go to project and set up programs arguments, because this is how you can specify the value you want to use to test the program. So you have to go to debug and go to program arguments and then put in -e followed by whatever value you want to use to test the program, like 2.34 e -100, and then click OK. Okay, because that is the same thing as you type it in when you run the program on the command line, and then you specify -e 2.34 e -100. So let me test run the program first, okay, because I want to show you what the program has done already and what you need to do to get your assignment done. So parse.c is already done. If you're interested in how I get the base 10 scientific notation parsed, you can read it, but there's nothing you need to do to change it. Same thing with main. So your code should go to exp1022.c. So this is the function where you need to make changes. And right now we just have to deal with negative exponent. So do not work on positive exponent until you're ready to do it. Okay, it's not due next Thursday. What is due next Thursday is for negative exponent. So what I'm going to do is I'm going to put a breakpoint here, okay, right there, because I want to see what is the structure pointed to by pn when we get here, because remember the number is supposed to be parsed at this point. So now I need to go to debug and run the program in debug mode. And has the program stopped? I cannot tell. Huh. Okay, so I think it went into an infinite loop. Okay, so maybe I need to read my own instructions in the lab, because it does specify here what you need to do. Oh, it's -n. Okay, I stand corrected. Okay, so I messed up my own program. So instead of a -e, you're supposed to put a -n. So that's why it went into an infinite loop. There we go. So this is really important, because if you don't do this part correctly, it will throw the program into an infinite loop. So change that, and then we're gonna stop the execution, and then we run it. So we go to debug, start, and this time it should stop. Yep. Okay, so we can see the yellow triangle, which means we have stopped. Oh, it's it's just a command. I forgot that I used -n to specify the following is the number to be converted, and instead I thought it was using a -e, which doesn't make sense at all. What is a -e? So now you go to the command, and then you can use print the structure that is pointed to by pn. And right here you can see the sign is 0, which means the value is non-negative. The mantissa is 234 as an unsigned integer. EXP10 is -102, which is a signed integer, and then EXP2 is initialized to be 0. So all of this stuff here is already done for you, because as soon as you get into this particular subroutine, you can make these assumptions. So what X was, okay, in the demonstration is basically mantissa. You probably have to review a little bit of how to access individual members of a structure that is pointed to by a pointer. That topic should have been covered in CISP360. Alright, so we are running out of time, but I still need to discuss how to do this with online GDB. So if you are planning to use your code blocks, it's done. The discussion is already, it's basically completed. On the other hand, if you say, I want to do this on a Chromebook where I cannot install a compiler or an IDE, then you will probably want to use online GDB to do it. So let me go to online GDB. The link to online GDB is in the assignment already. So this is how you get to online GDB. So just click on this link. It goes to online GDB. If you do not have an account set up with online GDB, I strongly suggest that you have an account set up, which is free. And if you think you do not want to expose your normal Gmail account with online GDB, just get a burner account. Okay, I talked about this before already. The restriction with online GDB is you can only have one single source file. Okay, unless they have made some changes, you can only have one single source file. Visual Studio, you have to find out how to do it in Visual Studio. I'm not familiar with VS Code or Visual Studio, so I'm not really sure how to do it. You can probably do a quick search and find out how to do it. So I can do a quick search here, which is VS Code set program arguments. And how do I pass arguments when I use VS Code to debug? So I think this is the... Okay, so one of the fields in the debug configuration is args, where you can use to pass the arguments. So there you go. So I think that answers the question in the text channel right now. There we go. And obviously you want to test it first. Okay. All right. So to use to use online GDB, you have to copy the entire monolithic code to that side. So let me start up another command line here. So if you download the other one, which is called monolith.c, it is just the one file version of the entire project. It's the same code as in the one for code blocks, except there's only one single file. So the way I do this here, because I'm using Linux, obviously if you're using Windows, it's going to be a different command. So I just have to cat monolith to xclib -cell clip. So basically, just copy the entire file into the clipboard of my desktop environment. So now I can go into the browser, select all, and then Control V to paste over the entire thing. So and the advantage of having an account already set up is you can save it. So I can now click on save. There we go. And I'm going to have to sign on again because it's not keeping my sign-on status. I just use my apps.losrios.edu account, to sign into online GDB. There we go. It's off screen, so I would call this a project call it negative exponent, right? Because that's the name of the lab. So now the nice thing is it's kind of like Google Doc, when you don't have to save it to your own computer anymore. So you can just keep clicking save when you have made changes. And also the command line arguments can now be specified here. So I want to show you a few things. Okay, if you choose to go this route, I want to show you a few things. The first thing is you need to locate where you're supposed to change, which is EXP10 to EXP2. Same thing as in the case of CoBlocks. You only have to deal with negative exponents for now. Okay, so you don't have to deal with positive exponents. So I'm going to do the same thing, which is setting a breakpoint here. And the nice thing about online GDB is it's pretty visual too. For the most part, you can actually set breakpoints and unset breakpoints using just the user interface. So now I'm going to click on debug. So do not use run, because if you use run, you won't have a chance to enter something. But on the other hand, if you use debug, it will give you the GDB interface where you can do a lot of stuff. So I'm not going to click. Oh, I forgot to set the language. It is C. So now it's compiling, and it complains about, oh, I forgot to change one of those things. So you might have to change this too, because I forgot that I have a pound include for something for header file, and you cannot have your own header file in online GDB, so you have to delete that line as well. So let's do it one more time. Okay, so I forgot a few of these. And every time you make a change, you can click save to make sure that you save the version. We'll try it one more time. Alright, so just get rid of all the pound include with double quoted file names. Save again. And one more. You're almost there. Almost. Save again. I can paste this, into the text channel of today to save you guys the trouble of having to find those lines and making those adjustments. Yep. I believe this may be the last one. Okay, I'm just gonna manually go through this because I can actually spot these things faster than the compiler. There we go. Main is the last function, so we're good there. Alright, so now we go to debug. And we have the debug prompt. Okay, so this is really important. When you are using GDB to interactively debug your program, the first thing is we need to set a breakpoint into to this line here. So when you run the program, okay, there's a okay, Rahu, your mic is on. All right, so now that we have set up a breakpoint over here, when you run the program, you normally just say run or just R. So in this case, because we need to specify -n 2.34 E100, so that means you have to type this part in every time you run your program from the debugger. Okay, so just run R -n 2.34 E -100. I typed 1000. Yes, so it's supposed to be -100. There we go. And then when you press the enter key, it now gets into main because I forgot to get rid of the original breakpoint. So it just went for it just remember using line numbers. So this one is okay. I can just do a continue, you'll see, or you can use one of these keys to continue execution. There are some shortcut keys to continue execution, maybe. Oh, right here. So continue is the same as just typing C, which will basically run to the next breakpoint, which is where I want it to be. So this is the same breakpoint as in the one in CoBlocks. So now we can say print whatever PN is pointing to, which is a structure. And oh, okay, it doesn't like that because I have to. I wonder whether I have to single step into it first. Okay, so I guess that's why it doesn't want it, because PM was not in scope earlier. Now that it is in scope, I can now see the members inside Pn has sine, mantissa, the exponent of 10 and the exponent of 2, and these are identical values compared to the one that we saw earlier in CoBlocks. Oh, I just passed it. There we go. Okay, so it's the same thing over here as what we saw over here. So are there any questions about how to use online GDB instead of CoBlocks? And if you use VS Code, it's going to be about the same thing, but you do have to find out how to set the program arguments. All right, so I think that's all that I wanted to talk about. This is due next Thursday at 9 a.m. As I said, get started early. And I'm not giving myself a pass today, since so I'll be around during the lab time to answer questions if people want to get started early. But do keep in mind that my office hour is right after the last of the lab. So that's going to be from what, 1:30 to 2:30, and then my communication policy is getting back to you in 24 hours. So for people who like to procrastinate, you have to plan how you can procrastinate all the way to the last minute, but not too much. Okay, so because in every single class there are a few people who want to really, really push it and expect me to stay up past 10 p.m. to continue to answer questions. I can promise you that is not what I am going to do. All right. So Richard has a question. Best procrastination plan. Get it done first, procrastinate later. Well, I have to say that I am a procrastinator myself, but I usually keep an eye on the deadline as I procrastinate. Okay, so there's that. I'll be online, all the way until 2:30. So if you have any questions related to what we talked about today, I'll be here to answer those questions. Other than that, I don't see any questions in the text channel that need my attention right now. So I'm going to stop streaming, stop screen sharing, get something to eat, and then I'll be back to keep an eye on the text channel.